Hey guys, welcome back to chapter 16. So what we're going to do in this video is we're first going to talk about water. And the reason we're going to start with water is it's going to help us to build our skill set so that we can apply these Ka and Kb values to get to something useful like pH. So this is going to be the slideshow where we are building our skill set in order to perform very well on pH problems. Okay, so we're going to first talk about water. So water is a very extremely weak electrolyte. So when we've got just a beaker of pure water sitting on the counter, there are actually some ions present. So we call this the auto-ionization of water. So water in and of itself does break apart into ions. What do I mean by extremely weak electrolyte? Well, 2 out of every 1 billion water molecules forms an ion. So it's very, very rare, but it does happen. And because it does happen, it gives us a springboard into this idea of pH. So here are the chemical equations to show this auto-ionization of water. So first, we've got our H2O molecule, and 2 out of every 1 billion molecules will do the following. So they will break down into ions. So they break down into hydrogen ions and hydroxide ions. Of course, if we have these hydrogen ions in the presence of water, of course, this hydrogen ion will latch on to a molecule of water and form this H3O. So again, these two are synonyms of one another. They mean the same thing, just a slightly different way. Okay. So what this means is that all aqueous solutions, excuse me, or all water solutions contain both hydroxide and this hydronium ion. Okay. Well, what do we see here? Yeah, we see these equilibrium equations, right? So with an equilibrium equation, we've got a K value, right? We've got these K values, the concentration of the products over the concentration of the reactants, okay? So what we see down here is that K value. So we've got the concentration of the products. So our products are the hydronium ion and the hydroxide ion over the concentration of our reactants. But what are our reactants over here? Yeah, our reactants are liquid. Our reactants are water. So do we include liquids in our K equation? No, we don't, right? We don't include those, okay? So then, if we don't include the water in our K equation, we've got a K equation that is so important, we actually give it its own subscript. So we replace this C value with the letter W. So this is the K value for water. And it is just the concentration of hydronium times the concentration of hydroxide. And we know this value, so this is a constant, right? We know this value has been very well researched. The value is 1 times 10 to the negative 14th. Okay. We call this the ion product of water. Ion product of water. Okay. So again, we're building a skill set here, okay? So the ion product of water, that Kw is the concentration of hydronium times the concentration of hydroxide, and it equals 1.0 times 10 to the negative 14th, okay? For water only, so for a sample or a beaker that has just water in it, the product, so remember product is just multiplying two things together, the product of hydroxide times hydronium will always be the same number. It'll always be that 1.0 times 10 to the negative 14th, Okay. That number is called the ion product of water, and we give it this Kw value because it's so important. Old school, so dissociation constant of water. So this is actually how I learned it when I was going through chemistry. So ion product of water, dissociation constant of water. Again, they mean the same thing. Okay. And then just to reiterate, all aqueous solutions contain both ions. Okay. All right, so we have learned that water spontaneously ionizes, so 2 in every 1 billion molecules will break apart into hydronium and hydroxide. We wrote the Kw value, so we can determine that constant, and it's going to be 1.0 times 10 to the negative 14th, okay? So what does this have to do with anything that we've been talking about? Well, this is going to lead us directly into this idea of pH, okay? So now we can apply what we know to acidic and basic solutions. One more thing to point out before we step forward is this equation right here. This is going to be kind of our baseline. So we know that water is neutral, right? It can act as an acid, it can act as a base, but just water by himself is a neutral compound. So if this is our baseline for what neutral is, we can look at, well, what happens up here and what happens down here, which one's acidic and which one's basic. That's what we're going to do now. So in a neutral solution, we would have equal number of hydronium and hydroxide. And this is what we see in water, okay? So if we have equal amounts of hydronium and hydroxide, that must mean they equal 1.0 times 10 to the negative 7. So how do I know this? Well, it's pretty easy algebra. Let me grab my stylus here. All right. So how do I know that this is in fact true? So if Kw equals hydronium times hydroxide, and this equals 1.0 times 10 to the negative 14th. If I want to determine the value of both of these, so neutral solutions, they have to be equal, then I can replace this with an x and replace this with an x because they're equal, they're the same. So this would be x squared equals 1.0 times 10 to the negative 14th. Take the square root, and x equals 1.0 times 10 to the negative 7th. We can prove this to ourselves. So we could take 1.0 times 10 to the negative 7th times 1.0 times 10 to the negative 7th. And if you plug that into your calculator, it will equal 1.0 times 10 to the negative 14th. So just a couple different ways that we can prove this statement to ourselves mathematically. Okay. All right, so if that's a neutral solution where hydronium and hydroxide are the same, what would an acidic solution look like? So in an acidic solution, we would have our hydronium concentration would be higher than our hydroxide concentration. So remember, an acidic solution has the presence of that proton, or if it's in a water solution, the hydronium. So it makes sense that this concentration would be higher than the hydroxide. That would make it acidic. Now, with that Kw equation, now we can determine, well, if this is an acidic solution, what would the concentration of hydroxide be? Okay. So we've got this dissociation constant, Kw, hydronium, times hydroxide, and that equals 1.0 times 10 to the negative 14th. Okay. In our acidic solution, we have said that the concentration of hydronium is 1.0 times 10 to the negative third. And we want to know what the hydroxide concentration is, and this is still equal to 1 times 10 to the negative 14th. Okay. So some pretty straightforward algebra here. To get hydroxide by itself, we divide by 1.0 times 10 to the negative third. Divide by 1.0 times 10 to the negative third. So those cancel. Just a quick programming note here. Anytime that you divide by this exponent, so 10 to the, it's a good idea to kill this with parentheses. So make sure that you put that in parentheses so your calculator knows what to do with these exponents. If you don't put it in parentheses, your calculator can mess up the order of operations. Okay. So plug this into my calculator. So I'm going to take 1.0 times 10 to the negative 14th divided by parentheses 1.0 times 10 to the negative third, close parentheses. And now I get that my hydroxide concentration is 1.0 times 10 to the negative 11th. And remember, concentration is molarity. Okay. So in an acidic solution, the hydronium concentration will always be bigger than the hydroxide concentration. And if we know the concentration of one of those, we can use the KW equation to solve for the other ones. Those are the two big take-homes there. One last thing I do want to just point out, because it's common error. So 10 to the negative third is in fact a bigger number than 10 to the negative 11th, or 1 to the negative 11th. So 1 to the negative third looks like this. Like this, okay? 1 times 10 to the negative 11 looks like this. Okay. So this is a bigger number than that, but the exponents sometimes get students all backwards. Okay. All right, so if a neutral solution, concentrations are the same. Acidic solution, hydronium's greater than hydroxide. Well, then a basic solution, hydroxide, ooh, this is backwards. It should be like this. Hydroxide will be greater than hydronium, okay? So in a basic solution, hydroxide will be greater than hydronium. Okay. Again, if we're given the hydroxide concentration, we could solve for the hydronium using that KW value. Okay. All right. So let's apply this to a problem. Let's practice this skill. So determine the hydronium concentration when the hydroxide concentration is 2.5 times 10 to the negative 9th. And then just one step further, why don't you go ahead and see if you can determine if it's acidic or basic. So go ahead and pause the video and try to work this one out. All right, so to solve this equation, we're going to start with that dissociation constant or ion product of water, which is the concentration of hydronium times the concentration of hydroxide, and that equals 1.0 times 10 to the negative 14th. Okay. They give us the hydroxide concentration, so I'm just going to plug that into our equation. And we are solving for hydronium. So So this is 2.5 times 10 to the negative 9th. And the product of those is always this. Okay. So to solve for hydronium, I'm going to divide by 2.5 times 10 to the negative 9th. So that cancels. Divide by 2.5 times 10 to the negative 9th. And we get that our hydronium concentration equals, so we'll take 1.0 times 10 to the negative 14th divided by parentheses 2.5 times 10 to the negative 9th. And that equals 4.0 times 10 to the negative 6th. And remember, that's a molarity because that's a concentration. Okay. So we solved for the hydronium concentration. Now we can compare these two numbers. So which one is the bigger number? Yeah, this one is the bigger number. So when hydronium is bigger than hydroxide, that gives us acidic. Okay. All right, so we solved our first problem using the ion product of water. Okay. Well, this is just walking us through the same thing. What does the concentration of hydronium being 4.0 times 10 to the negative 6th even mean? Okay. If you looked at that number, would you be able to quickly say that's acidic, that's basic? Probably not. Probably not. But what if I said the pH of this solution is 5.4? Would you be able to tell me if it's acidic or basic? Yeah, you'd probably be able to do that pretty quickly, right? So what we're going to do now is we're going to transition from this hydronium hydroxide concentration into the pH scale. So the pH scale is just a little bit more user-friendly. The numbers are easier. And it's also something that is a little bit more universal. So if I say pH is 5.4, that's easier for you to understand. Okay. So pH scale, nobody likes exponents. So the pH of a solution is going to be calculated in the following manner. So pH, you're going to take the negative log, and then you're literally going to type in whatever the number is for the hydronium concentration. So in our previous problem, let me not draw this, I have it on the slide. So in our previous problem, the hydronium concentration was 4.0 times 10 to the negative 6th. So I'm going to plug that into that spot in our equation. And here's what we would type into our calculator. So to determine the pH of this solution, I literally would type into my calculator, negative. Then I would find the log button, log. Then I would type 4.0 times 10 to the negative 6th, close that parentheses, and hit equals. So the pH of this solution is 5.39. So if we can solve for the hydronium concentration, then we can quickly use this equation and solve for pH. And we'll be able to go back and forth in just a minute. Okay. So pH is 5.39. Very clearly and quickly, that is an acidic solution. So just as a review, so pH scale, hopefully is something you've seen before. If it's not, here is your introduction to it. But the pH scale basically goes from 0 to 14. You will see things go negative. You will see things go above 14. It's just very rare. But pH scale goes from 0 to 14, 0 being acidic, 7 being neutral, and 14 being basic. Okay. So the lower the pH, the more acidic the solution is. So something with a pH of 1 is more acidic than something with a pH of 5. The higher the pH, the more basic the solution. And then neutral is at pH 7. Okay. So let's see if we can work another problem together. So determine the pH of the solution that has a hydronium concentration of 1.8 times 10 to the negative 4th. And then determine if it's acidic or basic. So go ahead and pause the video and work through that. All right, so pH equals negative log of hydronium concentration. So pH equals negative log of 1.8 times 10 to the negative 4th. So in this case, pH equals, so type into our calculator, negative log 1.8 times 10 to the negative 4th. And I get that the pH is 3.74. Okay. Is this solution acidic or basic? With the pH being under 7, this would be an acidic solution. It's an acid. All right. Well, when we were looking at that autoionization of water, we did have the hydronium concentration, but there's also this other side that has the hydroxide concentration. So that hydroxide concentration, while it's not used as often, the hydroxide side can still be used in the same manner. So we've got something called the pOH scale. So the pOH scale is the inverse of the pH scale. So again, it goes basically from 14 to 0. Okay. But in this case, 14 would be acidic and 0 would be basic. So this is just an inverted scale. So pOH, we solve it the same way, the negative log of the hydroxide concentration. And when we solve for that, we get a nice pretty whole number. Well, maybe a decimal, but a non-exponent number. And then the higher the pOH, the more acidic. The lower the pOH, the more basic. And the one thing they have in common is that 7 is still neutral. Okay. So a little bit backwards, but still useful to us, and still something I would ask from you. So the last thing that we're going to talk about in the slideshow is how we can tie this all together. So there is a relationship between pH and pOH. So much like there is a relationship between hydronium and hydroxide, there's also a relationship between pH and pOH. And that relationship is as follows. pH plus pOH will always equal 14. So for example, if we have, clean this off. For example, if a solution has a pH of 3, then we can use this very simple arithmetic to determine that the pOH is 11. This will be very useful for us when we're looking at weak acids and bases to be able to quickly go back and forth between pH and pOH. Okay. Another scale that you'll see, and I'll introduce this later on, is something called the pKa scale. So stay tuned for this. It probably shouldn't be here in the slideshow. Stay tuned for that. I will I'll come back to this. So that's it for pH, pOH, and your introduction.